2007, and that was me. A few pounds lighter. But I started for this slide because actually this was my last slide from 2007, and I will end up this talk with the same slide. And the reason for that is because during that process of working out the correlated environments in quantum error correction, I learned a couple of things. So for example, at that time, I was wondering if you could have some quantum parameter and have your computer protected against correlations. As you change this parameter, I found out, well, me and other people, right, that your threshold derivation would still hold if you satisfy some dimensional criteria. But then, when I look at this, it looks like very much a quantum phase transition phase diagram. So you have something that we call an upper critical dimension, where perturbation theory works, where your expansion works. And below that, below the upper critical dimension, you kind of don't know. I didn't know. But I could guess, based on the quantum phase transition schematic phase diagram, right, that there could be a region where the threshold could exist, but you need to sum up a lot of terms in order to see it. And another region where you could not compute at all, that correlations are so strong that will completely suppress your possibility to compute. Okay. So now let me start. So what is the motivation? Well, we are all here because we would like to protect quantum information against the environment. So there are a lot of strategies like the coherence-free subspaces, dynamical decoupling, topological systems, and quantum error correction, which is supposed to be very general. But from my perspective, what I find interesting in quantum error correction is that in a correlated environment, is that what you're doing is actually you're driving your system strongly and creating with that a new state of matter, a possibility of having a different state. Right? You have this is a strong correlated problem when you have a correlated environment with many body system, over many body system. So, as usual, right, I will start with the threshold theorem, which is the starting point of all these discussions, right? Because it tells us that if you're below a certain noise strength, we can process quantum information for arbitrarily long times, right? And usually in QEC, the traditional assumptions, right, are fast measurements, but they are not really fundamental. Fast gates, and they are not fundamental again, in my opinion. And error models, which probably, in fact, what the error models add probabilities and not amplitudes. So what happens if you start with a Hamiltonian? And if you start with a Hamiltonian and you still want to use those assumptions, you usually have to go and derive some Master equation and a notion of a local probability using a Markov approximation. So, but as Daniel Lidar, Robert Alecky, and Zanardi showed in 2006, fast gates, constant supplies of fresh condensates, and the Markovian bath may not be mutually consistent. So we may have a problem. We may have to choose our poison and choose two out of these three hypotheses. Right? So what happens in real systems also? Well, is that we most likely will have correlations in space and time. So you have your qubits evolving, and they will excite some photons or some phonons, and they start talking with each other. Okay. So correlations in space and time are everywhere. And we need to throw them out. We need to justify our assumptions. So are correlations really bad? So this is a back-of-the-envelope calculation. It's actually a very simple calculation to consider the pure dephasing bath with an ohmic spectrum acting on a logical qubit. So you have just a single logical qubit. Here I draw a 5-qubit code. And I'm calculating here the lower bound for the trace distance between no evolving at all, right, the perfect evolution, right, is a perfect memory, and this memory, this bath driving dynamics. And as you, so the scales here are set up, or you don't pay much attention to the numbers because the scales are set up to find this 1 here, so I turn at 1. So you start here only with memory effects, which for the ohmic bath are very, very small, very low. Right? They grow slowly because they are logarithmic in time. But eventually, as the spatial correlations started to kick in, you see that your trace distance, this lower bound for your trace distance, start to increase very fast. So what can I tell about this graph is that, well, if you start believing that your local error probabilities is small and completely forget that you may have spatial correlations, sometimes you can go out of your threshold value because of the spatial correlations. So you need to be careful with your statements about measuring errors in one qubit and putting a bunch of them together. So a lot of people actually work on this problem, and these are some of them. Actually, those are the actually created, forged the way that I think about the problem. Right? And especially Barbara Sterhall and Buckhart's paper was one of the special ones that I really enjoyed to read and learn quite a lot. So, but what really created the whole framework that I'm going to talk about was a completely different paper from Dorita Aronoff, right? Because in 2000, she wrote a paper where she was analyzing the threshold theorem as a quantum to classical transition. And she was saying that, well, if you are below a certain error probability, you're in the threshold limit, you have resilient quantum computation and strong integrity of your computers. So this is like a low temperature regime. You are in a quantum regime. On the other hand, when you are above this threshold value, your computer is a noisy computer. Actually, is well simulated by a Turing machine. And this is a high temperature regime or a classical system. So this quantum to classical transition actually motivated the way that I was thinking about this problem. Because, well, if I can imagine error probabilities as a temperature, right? So this is low temperature and high temperature. Can I add now a quantum axis here and think about what are correlations doing to this quantum axis, representing this quantum transition? So it certainly makes sense to think that there may be a quantum to quantum transition. Why? Well, because a quantum phase transition is defined by a qualitative change in the wave function of your ground state. Right? That's how you pick up Sachdev's quantum phase transition book, and that's what it's written there. So you have a ground state wave function, and it changes as a function of a parameter of your Hamiltonian. So in QEC, we are not talking about a Hamiltonian, but we have a driven, we are forcing a particular state, right, that we want to have out of the problem, right, to preserve during the computer evolution. In this sense, we are defining a quantum phase. We are defining that state that we want to preserve. And so when you have a correlated environment, the question is, can your correlated environment drive you away from that particular state that you want? And so that's how I start to think about this problem in 2007. So the Gaussian model, the noise Gaussian model, actually is based on the generalization of the spin boson bath. Right? You have a free Hamiltonian for the bath, which is basic harmonic oscillators, and an interacting Hamiltonian between the degrees of freedom of the bath and your qubits. You also assume that there are some correlation functions that obey a power. If it was an exponential decay, well, that wouldn't be a problem, because then you can define formally the Born-Markov approximation. So power laws are really the problem. And the Gaussian noise enters in the point that you need to decompose, for practical purpose, the endpoint correlation functions into products of two-point correlation functions. So the important parameters here that will show up later are D, the spatial dimension of your quantum computer, delta, Z is called the dynamical exponent, and delta is a scaling dimension of the interacting Hamiltonian. Okay, so how general is this model? Well, this can actually happen in many situations in physics, right? So you have electromagnetic fluctuations, phonons, charge fluctuations, and etc. But it does not cover everything. It does not cover a spin bath, for example. On the other hand, you can also think in a very general argument about this problem. You can think about or qualitative but general, that after doing all possible hardware solutions to reduce your decoherence, right? You do dynamical decoupling, dynamical decoherence-free subspace, you do everything, you end up still with some residual decoherence between your computer, the interaction between your computer and your environment. So you have this residual decoherence that it will happen. This environment is still very large by hypothesis, right? So it's very unlikely that the computer will have a strong influence in the environment, and the environment will be in a minimum of its local energy landscape. So now that it's in this minimum energy of its landscape, you assume an harmonic approximation to this landscape and linear between the computer and the environment, and that's how you get to that model. So this is actually a paraphrasing of the original Caldera-Leggett argument of how to derive the spin boson model. And so what I'm trying to say is that, well, eventually we will end up with something very similar to that. We may end up with something very similar to that after doing several layers of hardware protection to the system. So the basic assumption in 2007 was that, okay, I have a spin, but this a lattice of a set of spins or qubits, but they are separated by a minimum distance. And delta here is the time that takes me to do an error correction procedure, an error correction step. And so why they are separated by a minimum distance? Because I wanted them to have an identity to start with. I wanted to be able to define what I was calling the local error per qubit. So when I was doing, when you look at the array of qubits and time evolving, I could separate the correlations into two parts. Correlations that would happen inside an error correction period, and this will address the probability of having errors, and correlations that will connect different error correction periods. And so by separating these two, I was creating an expansion and defining a way to create an expansion of errors and correlations, right? So I would address the probability of having errors in certain positions in space and time, and I'll also add or compute how corrections due to correlations between errors in different error correction times would affect your result in the end. The calculation was to develop a systematic expansion that would include these correlations and to study the stability of this expansion as a function of correlations. So the whole point was that, okay, I started with a well-defined system, which is the state that I wanted to protect, and now I'll start to add correlations and see how stable this new perturbation theory is. So it turns out that, well, it is stable inside this region, which I was calling loosely as above the upper critical dimension. So now we have a threshold theorem with, for temperature, right, or for local error probabilities, which are well defined because the qubits are individual inside each one of those hypercubes of its boxes. And also now I have a quantum access to this graph. So sufficiently slow decaying, fast decaying correlation, sorry, the errors will not matter. The correlations will not matter. So, but what are these two phases? Do they really exist? So are they really there? And that was the question that I didn't know how to answer in 2007. What they mean, right? Can I really address those situations? And how to consider the problem of a dense set of physical spins, right, without this hypercube hypothesis? Well, it turns out that I need to change the question. And the reason that I need to change the question is very obvious, right? Because when you are in one side of a phase transition, you're looking into a particular fixed point of the Hamiltonian space, right? It's very hard to see what's in the other side of the phase transition. You need to sum an infinite set of diagrams, an infinite family to actually calculate anything on the other side. So starting from the perspective of fault tolerance quantum computation, starting from that point would not tell me anything for the other two sides, for the other two possible phases that I was guessing they may exist. So I changed the question now for something very different. So for how long can we compute using QEC? So do all the most favorable assumptions that you can do, and ask yourself, for how long can you actually compute? So the friendly assumptions, still we see works. There are no errors in the measurements. There are no errors in state preparation. There are no errors in gates. Quantum evolution with only known error syndromes will be taken into account. So I'm saying is that, okay, I will never measure any error in the computer. The computer runs flawlessly without any errors all the time. And what are the unfriendly assumptions? Well, I have a power law correlation in time and space due to the BAF. So what's left over, right? If I already assume that I measure no errors, so what do I have? Well, when you do QEC, right, you encode a physical qubit in a larger Hilbert space. And you have your correctable errors and also the uncorrectable errors. So what I'm saying is that, well, I will look at these uncorrectable errors, and these are the things that are going to evolve my logical qubit. So that's pretty much everything that will happen, only the uncorrectable errors. Everything else will be suppressed. Well, I will not take into account because I'm assuming that I'll have a perfect history of no errors at all. Right? So every time that I measure a set of atoms, I measure no errors. So from all the possible evolutions of the quantum computer, I'm confining myself to consider this one. Why this one? Because from the experience from 2007, I know that this one is the one that leads you to the last possible decoherence. So this one will lead you to the longest computational time available to you. Right? All right. So the example that I will take into account is the 5-qubit code. Can I use any other code? Yes. But this one is the smallest one, right? And so it will make things easier. So you take the stabilizer codes and also the stabilizers for the code, and also the logical words. And then you look up in this table here, and you see that you have certain third-order events that are allowed. And of course, there are certain events that are allowed because it's a distance 3 code. All right? So these third-order events here, which are products of the stabilizers and the logical words, are the ones that I will keep. Why I'll keep them? Because they are the lowest order in the coupling between the computer and the environment. So again, will give me an upper bound. So it's a very lower limit, a very long time limit for what's possible to compute or not. And how the qubits are organized in space? Well, I assume spatial locality. So is this fundamental? No. But it's useful, and it's also very physical. It's very physical because measurements and gates are hard to do. So you expect that your logical qubits will be very close together. Or the physical qubits that make out the logical qubits will be very close together. So I put them close together in a certain pattern, right? In a certain d-dimensional lattice. And now we look at the time evolution in an interaction picture. So we start with the usual Hamiltonian in the Dyson series, and you expand. And I expand just to first order. Why expanding in the to first order? Because I'm assuming that for short times, for inside the QEC period, the likelihood of having very high order events is small. So what I'm doing is that I'm creating an expansion parameter, which is the coupling between the BAF and the computer, times the QEC period. So I'm saying that this will be my new small parameter. And I will organize all the expansion from now on, from that point on. So I'm looking for a very large computer and very long times. I'm aiming to address this question. So, okay, you would just expand that, and you look back at your 5-qubit code, and you confine yourself to only the third-order events, the ones that are allowed by the 5-qubit code, right? So you're going to have, for example, 2 ZZ errors and an X error is allowed by the code. And here is your logical qubit operator. So inside of this logical qubit of measuring no error at all, I still have this quantum evolution to take on, to move on in time. Okay. So this evolution with no errors now can be reorganized into 2 parts. I have my 3 qubits, my 3 operators between the bath and the environment. And then you can break down in 2 parts. The first one, actually, it's a high-order correlation event. It tells, it's going to show here, it tells me that, okay, I can have the 3 spins flipped, this one, and this one, but they do not contract, they do not talk with anybody else in the same QEC period, but they'll talk with someone in a different logical qubit or at a different time. So when I do that, I can assume again spatial locality and realize that this is a smaller contribution to my sum, to my corrections. But on the other hand, I can have a contraction. I think this guy died. Okay. It is working now. Thank you. Yeah, so I can have a contraction between 2 qubits inside a QEC period. So for example, 2 X errors that talk to each other, and then the Z error that doesn't talk to anybody. Well, we'll talk to someone later on in the computer evolution. Okay. So these 2 X errors, for example, that talk to each other create a randomized coupling constant. And so now I have these higher order correlations here and also a randomized coupling constant. And my sum, and my QEC period evolution was broken down into these 2 components. Okay, so now I'm going to throw out these higher order correlations using this spatial locality assumption for my physical and logical. And I will keep only this drastic coupling constant. So what did I gain? Now I can re-exponentiate that operator and write an evolution operator for the logical qubits. So this is the evolution operator for the logical qubits that are time-ordered. I have my effective coupling constant here, the coupling between the computer environment that is coarse-grained now, and the logical qubit. So this is the evolution for the logical qubits as time goes by, following this very particular history of syndromes. Well, I got a lot from QEC. First of all, my coupling constant now is way higher order, order 3 now in the coupling between the computer and the environment. And also, the ultraviolet cutoff was reduced. It's no longer the bare cutoff. It's related to the time that it takes me to do a QEC calculation. So all these high-ordered frequency moments of the bath, they kind of went away. So, but what it bothers me with this expression, and what's the problem with that, is now I recreated exactly the same functional form that I had when I started. So now I have an expression for the evolution of the logical qubit that's related to the bath exactly in the same form as the original physical qubits were talking to the bath. So now how I'm going to compute this upper bound for the time available to do quantum computation? I will once again look at the trace distance. I will look at the trace distance between these evolution of logical qubits due to this interaction environment and this ideal density matrix when there's absolutely no evolution at all. Okay. So this tells me how hard it will be to distinguish the two by measurements. So the information lost by the single qubit, a single logical qubit, it's very simple to calculate because it became now a problem of a single spin. I don't have to worry about my 5 spins anymore evolving in time. I reduce everything to a single spin, and I can look it up into the books. And I just look up, and this is the expression. And these are the kinds of functions that you need to calculate. So you need to calculate the expectation value of sigma z and the expectation value of sigma plus, logical sigma plus. So the coherence function, you can go to many books, Vaz books, for example, and look it up. And this is the integral or function that you need to do. You just need to do this integral in momentum space to find out what happens. And this is the result. The result is that the trace distance now, depending on certain parameters of the environment, has 4 different possible evolutions. So for zeta, this function here, smaller than 0, actually it's independent of time. Where what is zeta? So is 2 times z is the dynamical exponent of your theory. So it's how time and space are related. S is related to that dynamical, the scaling exponent that I talked in the beginning. And D is the number of spatial dimensions of the bath. So if this is smaller than 0, then there's absolutely no dependence. There is this initial small decay of the trace distance, but after that, it doesn't go away anymore. It stays there. If zeta is exactly 0, then you have a log growth in what? The number of QEC steps that you're doing. So the trace distance starts to grow very slowly, logarithmic with the number of QEC steps. For zeta between 0 and 2, now it actually grows as a power law. And from zeta larger than 2, it formally diverges, right? Because it will depend on the size of the bath. So for a very large bath, actually, it will go, the trace distance will go to 1 very fast. So the result now, if you invert, so just what I said, if you invert that expression for time, so this is the number of QEC steps, and you assume that there is a maximum trace distance that you can tolerate between the ideal evolution and the evolution that you have due to this residual interaction between the computer and the bath, you found out that for this subohmic case, right, you have this initial decay of the trace distance, and eventually, doesn't work. Thank you. Initial. Oh man, you don't want me to finish this. Oh, there you go. So you have this initial decay, but after that, it doesn't decay anymore. And so if you start below the threshold, you're going to stay there forever. So on the other hand, for zeta equals to 0, you grow, but you grow not, the growth is not that bad. So pictorially, right? Oh, I'm going to talk later. So now what about an array of qubits? So to calculate the trace distance for an array of qubits, and now I don't have, I have a really spin array that is coupling to this bosonic path, and it kind of mimics a lot of what you do in solid state. So, but even to do that without having to worry about the QEC evolution and measurement and so on and so forth, everything was taken into account already. This is a hard problem. So I cannot do this for the trace distance. But I can do something for the Hilbert-Schmidt norm. And I can bound the trace distance with the Hilbert-Schmidt norm. Right? So n is the number of logical qubits, and this is the relation between the two norms. So the Hilbert-Schmidt norm can be written now in this form. And again, these are all the elements inside that matrix that you need to calculate. And you came again facing another integral in momentum space that you can do. So now I'm just going to need to calculate all these integrals here. And the result that you find is very similar to what you had before. But now you have the self-interacting part of the diagonal terms of the density matrix to look at. And this defines a particular zeta. And you have the correlated parts, the off-diagonal terms of that density matrix to look at. And this defines another zeta. So here, what the difference between the two for the correlations part, you also have a term that will depend on the dimension of your computer. So if you lay down the spins in a square lattice or in a cubic lattice, this will change this criteria here. Now, so when you go back, and then you see that you once again have 4 possible behaviors. A subohmic, where you have something that is independent of the number of QC steps that you're doing. And the other 3, which actually will depend on the number of QC steps that you're doing. So for how long you can compute? Well, you can invert those expressions and find out, well, if you start below the threshold for a superohmic bath, you can compute for an infinite amount of time, assuming all these good hypotheses that I did. If you are the ohmic case, then it grows, but doesn't grow that bad. So this is the critical distance that you assume that you can have to compute. And in the other cases, you start to go away really fast. So graphically, that's the pictorial thing that you have. So for a superohmic bath, you can go below, and if you start below the threshold at what you call a threshold distance, you go and you stay below this threshold. You have initial decay, and after that, you don't decay anymore. And on the other hand, for the ohmic bath, you eventually grow very slowly and eventually crosses your threshold distance, but very slowly. And finally, for the subohmic and adversary scenario, you go really fast away from this ideal evolution. So now, what this tells me? Well, this tells me is that first of all, there are adversary environments to QEC. So if you have correlated environments, depending on the interplay of the dimensions of the bath and the dimensions of the computer and the parameters that enter into it, you can have some environments that are really bad, that correlations actually will drive you away from your desired quantum state. In situations, in certain situations, it is possible to improve a lot by doing engineering on your qubits. You don't need to put them all together. You can put them apart. You can try to reduce all these effects. And so it is not an absolute statement that I'm saying that it is impossible to compute for certain environments. It just means that you need to rethink your engineering when you find certain situations. In all cases, the total logical qubits enter in the expression for the total amount of time available. But this is expected. So this is not something that you wouldn't expect. Even in a stochastic error model, that's what you expect. And the 3 regimes that I just described, they really enter in this qualitative interpretation of resiliency as a dynamical quantum phase transition. So what I'm saying is that, okay, so when you are in this superohmic regime, you are in this traditional threshold theorem limit, in a place that perturbation theory works fine, and you can expand in terms of the correlations and correct for the existence of correlations systematically. When you're in this finite, the ohmic case, or the upper critical dimension, is when you start to grow very slowly away from the regime, where you need to sum up an infinite family of logs in order to find a quantitative result. On the other hand, in this subohmic regime, you have a finite amount of time available to you to do the computation. And the reason for that is because all these leftovers, all these uncorrectable errors will start to accumulate and will drive you away from your ideal state in a fashion that is faster than logarithmic with the number of QC steps. Finally, if you are below this lower critical dimension, below this, so that condition for zeta smaller, larger than 0, it's not possible to compute formally. And why is that? Because all the expressions, they are suppressed by the size of the bath. As the size of the bath gets bigger, that you have available to compute becomes smaller. Okay, so that's it. Thank you very much.
Questions?
Thank you. Well, you started the same slide and ended the same slide as the previous time, and I actually have the same question as I had the previous time. There is a design of qubits that would allow you to couple to the bath not as a dipole coupling, but as a quadruple coupling, as an octuple coupling, etc. And that would reduce the delta a lot. And so in ion quantum computer, you would just use dark transition. In spin qubits, you just use spin up, spin down encoding, double quantum spins or triple quantum spins. And those would reduce them dramatically. Yes. And so the delta would go up, and so, you know, not possible to compute. That means unless you do some tricks which experimentalists are sort of very good at.
Yeah, I agree. So, but that's why I was trying to say when you started when I started the discussion, right? Is that, well, how generic this is. What I'm trying to explain, or better say to argue, is that this ohmic bath or this bosonic bath is very ubiquitous, right? After you do everything that you think about, the coherence-free subspaces, right, or dynamical decoupling, there will still be some leftovers. And it's very likely that we'll be able to model these leftover interactions by a bosonic bath. And so I'm not saying that these bosons here that I'm discussing are necessarily the electromagnetic fluctuations or the phonon fluctuations, but everything that is left over after you go to a logical or to a first layer of hardware protection.
So you did this analysis for the 5-bit code, but do you have any sense of where those two crossover points depend on the properties of the code?
So what the code will do to you is actually increase the power of protection due to this distance, right? So when you increase the distance of the code, that effective coupling constant will become higher power in the bare coupling constant. So in terms of the general analysis, nothing changes much. But the effective coupling constant will be extremely reduced by a larger distance code. That's why surface code seems to be good, right? Because the surface code will grow, the distance of the code will grow, right, as you grow the lattice. But on the other hand, the qubits are very close together, so there will be a lot of correlations there too.
I would just like to ask for clarification. Could you please go back to the slides where you show the curves as your quantum showing how your quantum information degrades over time?
Yes.
So there was the super ohmic case that seemed to be too good to be true. So you are not losing all quantum information in the limit of infinite time.
That's right. And let me just clarify that. It's because I'm assuming that I have an infinite computer, and I have an infinite amount of time that I'm computing, but also an infinite computer. So what I'm just saying is that and I'm assuming all these very, very good evolutions, these evolutions with high order in the bare coupling. So they are very dilute. So when you take the thermodynamical limit, these errors, these leftover errors, They are very dilute in space, and so when you calculate the trace distance, they will not take you away.
Okay, I'm just asking because even if you would use one of our phenomenological error models, totally independent in time, I mean, for such an error model, sooner or later, you would lose your quantum information in the limit of infinite time. You would lose everything. So you would, so you would end up with a completely depolarized density matrix. So I'm wondering about those other curves and about the slopes. So for those other three regimes, and you may have said it, what do the slopes depend upon? Do they depend on how many encoded qubits you have in your computer? What do it depend?
So the slopes here, they are actually they are just a figure, they would just draw. They are not really calculated, right? So because this is a quantitative statement. But if you go back and see what they really depend in terms of the code, as I said, is the distance of the code. The larger the distance of the code, so this longer time will take you to cross your threshold. So that's it. So the larger the distance, this longer time will take you to do that. So that's pretty much what I have to say. Right? About the superohmic case, is very as I think we discussed this before, is very much like when you calculate the echo and so on and so forth. If you have these superohmics, you can do the numerics, and you just oscillate it. You have an initial drop of the fidelity, for example, and then you oscillate it back and forth, back and
Any further questions? Well, we'll hear about that last point a little later today in one of the afternoon talks, but let's thank our speaker one more time.
Thank you. Thank you, Daniel.